Good morning to all, and my name is myself. I'm Art Joseph Paul, Assistant Professor, Department of Mathematics, SNS College of Engineering, Coimbatore. Today we are going to discuss about Cayley Hamilton's theorem. So first we are going to discuss about what is Cayley Hamilton's theorem and the statement of what is Cayley Hamilton, and we are going to discuss about its few problems regarding Cayley Hamilton's. So what is Cayley Hamilton's theorem? So Cayley Hamilton's theorem states that every square matrix satisfies its own characteristic equation. So here we are saying that for all the square matrix, so here that is the statement it's derived. Every square matrix, whatever are the matrices, let it be 2 by 2 matrix or 3 by 3 matrix or n by n matrix. We are defining the characteristic equation. Already we have discussed about what is characteristic equation in eigenvalues and eigenvector. When if it is 2 by 2 matrix, we are saying lambda square minus s1 lambda plus s2 is equal to 0. When it is 3 by 3 matrix, the characteristic equation of 3 by 3 matrix is defined as lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. We are finding s1, s2, s3 and we are substituting. So we are saying that for any square matrix, for every square matrix, it satisfies its own characteristic equation. It's called as the Cayley Hamilton's. So by using Cayley Hamilton's theorem, we can find order of a matrix, any order of a matrix, that its power of matrix, a power 4, a power 6, anything we can calculate. And also we can calculate its inverse of matrix by using Cayley Hamilton's theorem. So the first matrix it's given, I need to verify that it satisfies its characteristic equation for the given matrix. A is 1 minus 1 1 0 1 0 2 0 3, and we are finding its inverse and a power 4. So first we state that every square matrix it satisfies its characteristic equation. So first we are defining the characteristic equation. So the given matrix A is a 3 by 3 matrix. So we are defining lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. We are calculating s1, s2, s3, and we are saying that s1 is 5, s2 is 5 and s3 is 1. So the characteristic equation is going to be lambda cube minus 5 lambda square plus 5 lambda minus I is equal to 0. So now I need to verify this characteristic equation. So the statement is very well, we know that every square matrix satisfies its characteristic equation. So the scalar value lambda I am converting into A. So we'll have the form equation in the form of, when I am taking lambda is equal to A, we have a cube minus 5a square plus 5a minus I is equal to 0. So here a is given, I need to calculate what is a square and a cube. So a square and a cube it is calculated by multiplying its matrix value. So we are taking a square as a into a cube we are taking it as a square into a, we have calculated, and I need to substitute the values of a cube, a square in the characteristic equation, and I need to check whether it satisfies as 0. Its meaning is we'll arrive a null matrix. So by substituting the matrix a cube minus 5a square plus 5a minus I is an identity matrix. When we multiply a scalar value inside the value of a square and a, when we have an addition operation, we'll have a null matrix. So by that I can say a characteristic equation is satisfied. So we are saying the given matrix is a Cayley Hamilton's theorem. So we are saying it's satisfied. Next I need to find its inverse and a power 4. So here we know what is the formula of A inverse. A inverse is nothing but adjoint of A divided by determinant of A. So we should not use that formula to calculate A inverse. So here we are using the property of a Cayley Hamilton's theorem to find the A inverse and adjoint of A. That is a power 4. So to find A inverse, we are multiplying by A inverse on both the sides, that is we are pre-multiplying it. So when we pre-multiply A inverse on both the sides, in the characteristic equation we have a square minus 5a plus 5i minus a inverse is equal to 0. By keeping a inverse on my left hand side and I'm taking the remaining elements to my right hand side, we have a minus a inverse is equal to minus a square plus 5a minus 5i. So by multiplying my minus on both the sides, we'll have a inverse is equal to a square minus 5a plus 5i. We know what is a square and a and I, so we are substituting that. So by that we'll arrive the value of a inverse. So the value of a inverse, we are saying it as 3 3 minus 1 0 1 0 minus 2 minus 2 and 1. Next we are finding the a inverse. Similarly the same, we are not multiplying a power 4 is equal to a square into a square. We are using the property of Cayley Hamilton's theorem. So we are multiplying a, pre-multiplying by a in the equation 1. So we have a power 4 minus 5a cube plus 5a square minus a is equal to 0. By keeping a power 4 on the left hand side, the remaining values are taken to the right hand side to calculate the value of a power 4. So the value of a power 4, we are saying it as 41 minus 16, 56, 0, 1, 0, 112, minus 40 and minus 53. So this is how we are calculating the value of a inverse and a power 4 by using Cayley Hamilton's theorem. So similarly we can find for some more problems also. Thank you. We'll see you in the next class.